At the moon's south pole lies a place stranger than any desert on Earth, where sunlight never reaches, temperatures plunge below minus 240 degrees Celsius, and invisible electricity silently gathers on the stones, turning the hunt for water into a perilous engineering challenge. The moon has always fascinated us, bright enough to show craters with the naked eye, close enough to feel familiar, yet still hostile. We walked there decades ago, but understanding its water and the places that hide it is only just beginning. Water is the key. It means air to breathe, fuel to burn, and shielding from radiation. The same physics that lets water launch rockets also holds your feet to Earth, linking everyday gravity to the grand logistics of exploring the solar system. Early missions hinted at something unexpected. In 1976, the Luna 24 probe drilled about 2 meters down, returned soil, and scientists detected tiny amounts of water that increased with depth. They dismissed it as contamination, and the moon kept its secret a little longer. Clementine changed the story in 1994. It mapped the poles and revealed permanently shadowed craters, regions that have not seen direct sunlight for billions of years. At minus 173 degrees Celsius or colder, they looked like natural freezers where ancient ice could survive indefinitely. Lunar Prospector followed, measuring hydrogen at the poles from orbit. The signal hinted at tens to hundreds of millions of tons of water ice mixed into crater floors. Yet when Prospector crashed near the pole, Earth-based telescopes saw no clear spray of ice at all. Japan's Kaguya later mapped the moon in exquisite detail, but still could not directly spot ice in those polar shadows. It too ended its mission with a controlled descent, hoping ejecta would betray hidden water. Again, no unambiguous signature. The puzzle only deepened further. In 2008, Chandrayaan-1 tried a different tactic. An impactor slammed into a polar crater, while instruments sniffed the thin exosphere above. Spectroscopy finally confirmed water in gaseous form, and its moon mineralogy mapper later found water and hydroxyl bound in surface minerals across the globe. NASA's LCROSS pushed harder. It drove a spent rocket stage into a permanently shadowed crater, then flew through the resulting plume. Instruments detected hydrogen, water ice, ammonia, methane, and other volatiles. For the first time, polar craters were confirmed as genuine cold traps full of resources. Today, estimates suggest around 600 billion kilograms of water ice on the moon. Sunlit regions can bake at 127 degrees Celsius, yet nearby shadows drop below minus 200. That contrast, combined with the moon's tiny axial tilt, lets some crater floors remain cold enough forever. So, where did this water come from? Ancient comets may have delivered it. Micrometeorites still pepper the surface with traces. Solar wind protons can react with oxygen and minerals to form hydroxyl, later converted to water by high-energy impacts, then trapped between grains of regolith. LRO also found the whole moon is slightly moist. Trace water molecules migrate across the surface, accumulating in cooler regions by night and thinning around local noon. Suddenly, viable sites for bases expanded beyond the deepest shadows, since even sunlit soil carries a whisper of water. Then came a startling measurement. LRO's Diviner instrument recorded some polar crater floors at about minus 250 degrees Celsius, colder than Pluto's average surface. These pits are among the coldest places ever measured, perfect natural refrigerators that can preserve ice and volatile molecules for eons. Yet those same craters create another extreme. Solar wind particles skim the polar regions almost horizontally. Lightweight electrons race down into the shadows faster than heavier ions, coating crater walls and floors with negative charge, while a region of positive charge forms higher above them. This separation builds intense electric fields. Models indicate surfaces inside some polar craters could charge to hundreds of thousands of volts relative to surrounding plasma. No sparks in vacuum, but that potential can arc across equipment, disrupt electronics, and create a uniquely hostile electromagnetic environment. For future explorers, these pits become the most dangerous places on the moon, not because of cliffs or monsters, but because invisible charging could silently stress spacesuits, rovers, and drills, exactly where the richest ice deposits are expected to lie beneath the frozen regolith. There is a second hazard. Lunar dust, or regolith, is composed of razor-edged glassy grains that cling electrostatically to everything. Apollo astronauts reported it sticking to suits, scratching visors and seals, and irritating eyes and lungs when it hitched a ride back into the cabin. Apollo suits used woven Teflon. In laboratory tests with lunar soil simulant, this fabric easily accumulated charge and showed increased electrical arcing. The suit effectively bridged negative ground and positive plasma overhead, much like rubbing your feet on carpet then touching metal, only far more energetic. Why did Apollo crews avoid serious shocks? Their landing sites basked in continuous sunlight, so photoelectric emission kicked electrons off the surface, making it slightly positive and partially canceling the solar wind effect. At the poles, deep shadows interrupt that protection and let charges build. Keeping astronauts safe will demand new suit designs. Layers must conduct charge away without freezing stiff in -200-degree cold, or softening in +100-degree heat. Materials need to shrug off sharp dust, resist arcing, and still flex reliably through thousands of movements. Engineers are also inventing ways to keep bases clean. Experiments show bursts of liquid nitrogen can trap and remove dust from surfaces. Electrodynamic dust shields use pulsed electric fields across panels to coax regolith grains to hop away, clearing windows, visors, and solar arrays efficiently. Other teams are developing human-machine interfaces that let astronauts control rovers and robotic arms with simplified gestures from inside protected habitats. Machines could descend into the electrically charged shadows, drilling for ice and sampling soil while people remain in comparatively benign sunlit surroundings. Why accept all this complexity? Because water is the oil of space. Split into hydrogen and oxygen, it becomes powerful propellant. Launching fuel from the moon's shallow gravity well would be far cheaper than lifting every kilogram from Earth's deep and expensive gravitational pit. Alongside water, polar regolith may host helium-3 from the solar wind, plus titanium, iron, aluminum, and trace rare Earth elements. None are magical, but mined in situ they could support construction, life support, and energy production without shipping every brick and bolt from Earth. Plans from several space agencies now converge on the South Pole. Robotic stations, then human outposts, are aiming for ridges with near-constant sunlight and nearby shadowed craters. Yet mining rights remain legally murky, making the detailed mapping of every promising ice deposit increasingly urgent. The Volatiles Investigating Polar Exploration rover, or VIPER, was meant to roam those regions and drill below the surface. Its cancellation removed a key pathfinder. For now, we rely on orbiters and a handful of landers to interpret the polar environment from limited vantage points. South Korea's Danuri mission, carrying NASA's ultra-sensitive ShadowCam, finally peered into the polar darkness directly. Images of Shackleton Crater revealed textured hummocks and boulder tracks, but no bright glare from exposed ice. Either it is buried, patchy, or locked in grains too fine to sparkle. India's Chandrayaan 3 went a step closer, landing near the South Pole. The Vikram lander and Pragyan rover operated through a single lunar day, racing the coming night. Their instruments could taste the regolith directly, sampling soil that had never seen human hardware before. Pragyan's spectrometers found aluminum, calcium, iron, titanium, and the first in situ detection of sulfur at the pole, hinting at ancient volcanism. Yet hydrogen, the clear fingerprint of water ice, was absent in the top layer where its wheels and instruments could reach. Vikram's Chang'e probe offered a clue. It measured about 60 degrees Celsius just above the ground, then saw temperatures plunge to around -10 by 8 centimeters depth. Regolith is an excellent insulator, suggesting any stable ice may lurk just below the surface, shielded from heat. So the moon's water hides in buried pockets, tiny beads, and ultra-cold traps that also harbor extreme electrical environments. To tap it, future machines must descend into the quietest, coldest, most electrically active hollows on the moon, turning danger into a stepping stone outward. Right now, light reflecting from that same moon reaches your eyes in a fraction of a second. One day, fuel lifted from its most forbidding craters may power journeys far beyond Earth, and the universe and beyond will have watched the first cautious steps begin.